We're continuing with Boyle's law. In the previous two videos, we had learned the introduction. We learned from there to the experimental observation as well as the graphical representation. In this video, we are going to be talking about the practical significance of Boyle's law. So when we learned, okay, let's go back to the equations that we've learned. P is directly inversely proportional to 1 by V at constant temperature and a fixed amount of gas. Now, P equals to K1 by V. This is obviously again in the fixed amount of gas as well as temperature. So when we have a given mass of gas and we compress it, the same amount of gas is actually occupying lesser area. To make things clearer, let's assume this is a beaker filled with gas and this is at a constant temperature and obviously the fixed amount of gas. So when we push, so these molecules are going to be far apart, right? Now when we push the beaker, when we increase the pressure rather, what we notice is that all these intermolecular spaces are going to get really close and these gases are getting closer to the molecules of this gas are going to get close together. So when the pressure is increasing, the volume is decreasing. That is what we've learned all across Boyle's law. But there is also one more thing which is increasing. If you notice, the density is increasing from here to here. So here it is actually less dense, but here the molecules are very close and it is more dense. So what we notice, first of all, we know that density equals to mass by volume. We are just going to substitute this equation. So V will be equal to K1 by P. Right, so we will substitute the value for volume. So density is going to be equal to mass by K1 into P. Now mass is not going to change, right? Because the amount of the gas is the same, or the quantity is the fixed amount. So the mass and K1, these both are actually constants. So we can write this as K dash P. So at a constant temperature, pressure is actually directly proportional to the density. So density and pressure are directly proportional to each other, and this is at a fixed mass of gas. So one more thing. So this obviously means that when we are at a sea level, the density of the air around us is actually pretty high. So the air which we breathe in is actually quite dense. But if you notice, as you go up the higher altitudes, there might be a slight difference in the amount of oxygen, and even at even higher altitudes, like for example Mount Everest, the atmospheric pressure is 0.5 atmosphere and the oxygen becomes actually quite insufficient for us to normally breathe, and this causes something called as altitude sickness. So mountain climbers tend to carry the oxygen cylinders. Not only that, they undergo a lot of training to deal with such extreme conditions. So this D and P being proportional to each other actually shows that at sea level density is actually high, so the amount of oxygen available for us is high. But as we go to higher altitudes, the density is lower, and so because the pressure is low, the density is also low, so the oxygen available is insufficient. There's one more thing that I'd like to say before we finish up with Boyle's law. So the Boyle's law is only for a hypothetical gas called the ideal gas. We'll be learning about this in detail in the when we talk about the ideal gas equation, but this is a hypothetical gas. So for example, let's take nitrogen, oxygen, carbon dioxide. All of these gases obey Boyle's law only at low pressures and high temperatures. So at low pressure and high temperatures, gases like carbon dioxide, oxygen, nitrogen, all of these obey Boyle's law because they act as an ideal gas. At higher pressures and lower temperatures, these gases don't obey the Boyle's law. If you remember when we had talked about pressure versus 1 by V graph also, I said that when we have it a higher pressure, the Boyle's law might not be followed. So with that, we're done with the basic understanding behind Boyle's law. In the next video, we'll just be doing the in-text question of Boyle's law. Do check it out.